Hello everyone. Last video we went over the proof of a Laplace theorem, which says that the Laplace of f of t is equal to 1 over 1 minus e to the negative s capital T, where capital T is the period, times the Laplace over one period, basically. The integral from 0 to capital T of e to the negative st f of t dt. So the proof I gave was not very rigorous, so therefore I wanted to do another video kind of demonstrating a bit more rigorous of a proof. So first of all, let's talk about what sufficient conditions for the existence of a Laplace. So we say that f is of exponential order. This is one of the conditions. F is of exponential order. C, if f is said to be of exponential order C if f is less than or equal to m e to the ct, where m, comma c, comma, I'm going to say star, is greater than 0. Oh, why did I say star? Well, what I was looking at had t, so I don't want to, capital T, I don't want it to confuse you, so we're going to say there's some point star, and that this is the exponential function. It climbs pretty rapidly. Let's say there's some other function. So this is f of t, and this is m e to the ct, right here. So at first, this is higher, but there, this should be right about there. So there is a point at which m e to the ct grows faster to infinity than f of t. It's sort of like the turtle and the hare in the end. M e to the ct wins out. So an example of functions that are of exponential order are anything like 2e to the 2t, sine t, anything like that. Because here you see this is the m, this is the c. They fit the form, m e to the ct and sine t, any regular function. So what's not of exponential order? Something like e to the t cubed or e to the t squared are not of exponential order. So that's the idea of exponential order. And that's one condition. The other condition is that it's piecewise continuous. I'll abbreviate it PWC. So we say a periodic function is piecewise continuous if it is piecewise continuous on every bounded interval of the form a comma b. So in our case, it's going to be 0 to t, and t to 2t. There's always these bounds at which it's stuck inside of, you could say. So so what is piecewise continuous? Piecewise continuous means that the limit of a from the right exists and limit of b from the left exists. Okay? And f is defined and continuous at all points except for maybe a finite number of points where the left and right hand limits exist. So basically what this says is you have something here, and you could have, maybe it's defined there, maybe this is not defined there, not defined here. Well, that's okay because it's only a finite number. So it may contain a point, or it may not. You know, you might have just it's undefined at that point. But with integration, we're not concerned with the point. We don't integrate over a point, so that's okay. So you know, you can have all kinds of crazy stuff, you know, going on, but this is a piecewise continuous function. So all that to get started on the problem. Alright, so we'll start again with the definition as we did in the last video. Laplace of f of t equals the integral from 0 to infinity of e to the negative st f of t dt. This is the definition. So how can we split this up? Well, we're going to split it up into a sum of the integrals over the intervals of length t, which capital T is the t, I mean the period. So this is equal to integral from 0 to t, capital T, e to the negative st f of t dt, plus integral from t to 2t, e to the negative st f of t dt, plus, I'm going to come down to the next line, 2t to 3t, e to the negative st f of t dt, plus dot dot dot, means we're just, there can be so many terms, we don't really care how many terms, any finite number, plus integral from n minus 1 to the n to nt of e to the negative st f of t. So this is arbitrarily large limits, and then we don't stop there, but we say plus dot 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 to say that it goes on for all infinity. Now we're going to leave this first integral alone, and we're going to look at this one, and we're going to say so for second integral, I'm going to abbreviate it int. For second integral, let u equal t plus capital T. For third integral, let u equal t plus 2t. For fourth, let u equal t plus 3t. For nth integral, let u equal t plus n minus 1 times t. Oh, I had this wrong. It should be minus. T minus. So in the last video, I had tau plus capital T equals t, and this is a different version of it. Sorry about that. So it's t minus capital T, and so on. So it actually was a substitution. Instead of tau, if we just put u in there, it was tau plus capital T equals t. We're just bringing the t to the other side, so it is a u substitution. Sorry about that. So here is our new limits, and if we plug in for the first one, capital T, the lower limit, minus t is 0, 2t minus t is t, so it's 0 to t. Let's look at the third. So plugging in 2t here, we get 0, 2t minus 2t, 3t minus 2t is t. So we have 0 to t at every one. You can plug, for this last integral, you can plug this in if you want, and you can see you get the same limits. And it's convenient because notice it corresponds to the first limit, 0 to t. We can rewrite this now as Laplace of f of t equals integral from 0 to t of e to the negative st f of t. That's the first one, just bringing it along for the ride, right here, first one, plus e to the negative st, capital T, and we're just using the u substitution, we're just taking out the t from it for the first one. I did this in my last video. You can watch that and review how I took that out. But we have e to the negative st, e to the negative su, f of u plus t, u plus capital T. Notice, looking at this first one, if we pulled this t to the other side, t would now equal, what was f of t will now equal u plus t, capital T. So that's what we're doing here, and plus e to the negative 2 st, integral of e to the negative, and I need to put the limits on here, but each limit is 0 to t, 0 to t, e to the negative su, f of u plus 2t, du, I don't know why I put t there, sorry, du plus dot 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 plus e to the negative n minus 1 s capital T, is the integral from 0 to t of e to the negative s u f of u plus n minus 1 times capital T du plus dot dot dot. So now, using the fact that f of u plus n capital T is equal to f of u, okay, and that's because it's a periodic function. You can watch my last lecture, and I put a little note in there. I had it as t plus capital T, but really equals f of t, but you can generalize it and say t plus n times capital T equals f of t. And we're using the fact that the integral from 0 to t of e to the negative st f of t dt equals integral from 0 to t of e to the negative su f of u du. They're just dummy variables, as I also mentioned last lecture. And factoring. We have integral from 0 to capital T of e to the negative st f of t dt. So we're switching back now because it doesn't matter. We have it in the same form. So integral is 0 to t e to the negative st f of t dt. And for the first one, it's just going to be 1 times itself. If you go back, the first one is just itself, plus e to the negative st, capital T, plus e to the negative 2 st, plus dot dot dot, plus e to the negative n minus 1 s capital T, plus dot dot dot. And some of you may notice, I'm sure you've taken Cal 2 at this point, so in Calculus 2 we learn about infinite geometric series, and this is a geometric series with the common term. So alright, infinite geometric series with common term e to the negative s capital T, and converges because e to the negative st is greater than 0 but less than 1 for s and t greater than 0, which we are assuming they are. So the sum, in quotation marks, because it's an infinite sum, but it's still a sum. So the sum is 1 over 1 minus e to the negative s capital T. Okay? It's a convergent series. And Now we can write, well, we have arrived at the proof here. We can say, therefore, the Laplace of f of t, where f of t is periodic, equals 1 over 1 minus e to the negative s, capital T, times the integral from 0 to capital T of e to the negative s, t f of t dt. And it checks out with what we have. So there you have it. A more rigorous proof of the Laplace transform of a periodic function. I hope, if anything, this video has helped you to appreciate the art and science of proofs a little bit more. I know it has for me. Thank you for watching.